This is a good initial image just to get started with. Most of the, the bitmasks that I'll be covering in today's examples are more than just 8. What you see here is an 8-bit bitmask. So by 8-bit, I just mean that there are 8 ones or zeros in order. And so in some of the imagery, you may find 12-bit, you may find 16-bit, but in each of the cases, the concept is pretty similar. What you have to do is take a look at to convert to understand what the bitmask is saying in terms of in binary terms. You need to essentially take a decimal value, which when you query when you use your inspector tool to query an image in Earth Engine, you'll essentially get a decimal value. So that can be the thing that is initially confusing. So for example, I have here, I'm looking at a modus image, and within that modus image, you're looking at a state QA band. So within, so state QA, let's move to the documentation for a second. Um, So state QA, you can have a look here, and in the documentation, it shows that it's a 16-bit bit mask. So all the way from 0 based indexing all the way up to 15. But when you query an Earth Engine image, you see with state QA, you see a number like 8397. And that is in fact a decimal number. It's not a binary. It's not directly shown here as a bit mask with the number of ones and zeros. What you can easily do there to interpret that is take your calculator that each of you have in your PCs and go switch to maybe programmer mode and type in your number. So here it says 8397. So that's the decimal number as 8397. But you can also see the binary representation down here below. So that is a 16, it shows you a 16-bit binary number. So now we'll get into how do we interpret that binary number. So I'll start quickly just with an example from with Landsat actually. So say, so within this Landsat imagery, you have 11 bits, right? So, and when I said earlier that there are generally 12 or 16 bits, there may be fewer than 12 or 16 bits that contain the information that is important. But anything after the 10th bit here would essentially be, can essentially be filled with zeros. But the bit mask information would be stored as a total of 12 or 16 bits. So in this case, say we want to, what we want to really find out is where is the presence of clouds or cloud shadows. So Landsat surface reflectance imagery, that's the documentation that we're looking at here, has already been provided with along with this pixel QA band, and that band has been generated after running the CF mask algorithm, which is a cloud masking algorithm, and you essentially get this pixel QA band as a result of that. And within that band, if we want to mask out clouds, if we want to use that band to mask out clouds or cloud shadows in our resulting Landsat imagery, what we need is essentially only the 5th bit and the 3rd bit. So essentially, what we need to do is a 3-step process. So I'll move to the code here. So this code, there are examples to the example scripts which show you how to run this code in the docs, in the slides that have been shared with you. So essentially, we're declaring a function, and within that function, we're declaring two masks. So the first mask is just um, this one and a double less than sign and a three. So this notation may be a little unfamiliar to some people in case you've not worked with it before. But this is called a bitwise left shift operator. So essentially, what you're telling this, what you're declaring this variable as is initially declaring it as a one, but then you're saying left shift that one by three spaces. So once you take, once you do that, what you get is the cloud shadow bitmask with in this form. So the one you can see here has been left shifted by three spaces. So it was originally in the units sort of place, but then it's been moved three spaces to the left. So that will essentially help you get your cloud shadow information. Similarly, the cloud bitmask um, has a one, but it's shifted five spaces to the left. This is again because um, your cloud information is in bit 5, your cloud shadow information is in bit 3. Um, so then what we do is evaluate it using a longer conditional operation, wherein you just take the QA band, which may be a completely long, is a 12-bit, 16-bit band, and you're extracting just the two individual pieces of information that you want. So, and you're making it a binary band. So what I've said here is declare a variable called cloud yes no. So that is essentially taking the QA band and using a bitwise and over the cloud shadow bitmask, and then using that same uh, bitwise and over the clouds bitmask. So only if both the cloud shadow is one and the cloud bitmask is one, um, sorry, is zero, not one. So if only if both the cloud shadow bitmask bit of information is zero and the cloud bit of information is zero, will it declare it as a um, valid pixel essentially. And then the not equal to here is just to reverse it. So reversing the one to a zero. Um, then essentially you return that image with these two bands. So that I'll take a look at what that looks like here. Give it a second to load. Yeah, but you can see here that this is a Landsat collection that's mosaic, and you're looking at the true color visualization initially. And on top of that, you're looking at the cloud yes or no band that was generated using the 2-bit mask. So essentially, wherever it is a clear pixel, you'll have a 0, and wherever it is a cloudy pixel, you'll have a 1. So that's what you get after um, after running this little script here. Now, similarly, if I wanted to do the same thing for a Modus composite, so Modus has these 8-day composites that are published, and within that, it has within that imagery, it has a band called State QA. So within State QA, there are additional bits of information. It's not just cloud related, cloud or cloud shadow related information. There's also land, water. There's also if I switch quickly here, there's also land water. There's also aerosols as the type of cloud and some other stuff. But we're only going to essentially take a look at clouds in this example here. Um, but what I'm telling you can equally be applied to look at the other bits of information other than the cloud bits. So here for the modus imagery, for the cloud bits, we're essentially looking at 0, 1, and 2. So in this case, I'll switch to the code. This is just a slightly different approach to generating the bitmask, but essentially, what you have to keep in mind is that what you want at the end is something like this that's shown here at the bottom. Um, because and so this is 1 1 right at the end. So why do you want this 1 1 right at the end? That's because your state QA band has the cloud information in bits 0 and 1. Um, and this is unlike the Landsat imagery, which had your cloud information in a single bit, which was bit 5. Here in the modus imagery, it is in 2 consecutive bits, 0 and 1. So essentially, what we're going for is generating a bit mask which is 0 everywhere except for the last 2 bits, which are both ones. So essentially, you declare what that boundary is that you want um, bits from 0 to 1. So you declare cloud QA start and end, and then your initial bit mask is 0, and then you run a for loop which gets you from QA start to QA end. And this is just a simple operation where if I say, I'll show you one initial example. So if you say 2 to the 0th power, that's essentially 1. So bitmask in the first instance of the loop goes from the initial value of 0 plus 1. So in the next iteration of the loop, your bitmask is already 1, and then you're adding to that 2 to the first power. So that's 2, and again that's 2 as a binary number. So essentially, what you're doing is, sorry, so this allows you to sort of declare any number of bits that you want um, in your calculator. So you can essentially, in the first instance, you're taking 2 to the first power, um, and then in the next instance you're taking, sorry, switch back to this. 2 to the first power, so that gives you 3. So 3 in binary you'll see is 0011, which is your bit mask that you're going for. You just have to imagine a certain number of zeros to the left of that up to 16 bits. So that's another approach to get the bit mask, but the concept is pretty similar. And then everything after that is also again similar, that you take your bit mask, and in this case, because your bit mask is 2 bits rather than 1 bit, you have done the operation slightly differently, because what you'll see here is that only 0 and 3 are clear. 1 and 2 is cloudy or mixed. So essentially, I've done a bitwise XOR, exclusive OR, with the band and with the number 2. So what is the number 2 as binary? That is essentially 0010. So that basically is saying that um, only isolate pixels that are not cloudy. So we're only eliminating one here out of the entire combination. If it is a mixed pixel, if it's not set, if it is clear, we're preserving those pixels with the bitwise XOR band. And then not equal to is again to reverse it. And then what you get here at the end is, show you that result quickly. This is the true color visualization. And the cloud yes or no band on top of that. So everywhere where it is black is essentially uh, is essentially cloud free. So what you'll see is that the modus cloud mask is much more stringent than, no wait, did I say that right? Yeah. So it's the reverse. Everywhere where it's white is cloud free in this image. Yeah. So the modus cloud mask is much more stringent as compared to the Landsat one, but essentially you get the results that you want. So yeah, that was a little bit of a primer, and